Welcome to this course on design principles of RF and microwave filters and amplifiers. So, the first week theme is microwave filter design. Today is the first lecture. Here we will not enter into the microwave filter design, but before that we will today see image impedance based filter design. Basically, this is radio frequency filter design at a much lower frequency than microwave filters. Microwave filters are starting from gigahertz, etc. We have already seen in earlier NPTEL courses that at microwave frequencies the wave propagation is not TEM only, there are TE, TM, etc. waves are all modes are also generated in microwave. So, microwave filter design should account for that, but before that already you see when radio was invented, even before that when telephone was invented and telephone circuits were developed, there was a need to design, analyze the filters that can separate one frequency from another. Think of this airspace, many radio stations are transmitting radio signals here. Now, if I want to listen to a particular, suppose All India Radio, I need to tune my receiver, radio receiver for that. So, out of various frequency signals, we tune to a particular frequency RF signal. To do that, we require a tuner, which is nothing but a LC filter. In your basic BTech courses on electronics engineering, you have seen RC filters, a simple RC circuit or CR circuit or LR circuit or RLC circuit, they also are used as filters, but all of them are lossy filters because of the presence of the resistance. But in a radio frequency transmission, reception, etc., there we need to maximize power. So, we do not use any lossy filter there. So, the basic premises of our filter design of our RF filters is lossless filters. Now, you know that if you have an LC circuit, it is a resonant circuit, it has an high Q. So, for a at a particular frequency which we call very narrow band, the filter tunes and then receives the signal, which is the case with the radio receiver filter. But there are applications where always we do not need such high Q, or we need to have a band of frequencies which need to be passed and all other bands to be suppressed. So, a narrow band LC filter or a resonant circuit, first order resonant circuit, LC circuit cannot serve that purpose, because it just selects one frequency, suppresses all other frequencies. So, RF filters, by that we mean that there should be a band of frequencies which we will specify, and accordingly filter will pass that, and all other frequencies it will try to suppress. Ideally, all other frequencies should be attenuated by infinite amount, but no real filter can do that, but it will be attenuated to sufficient amount so that it does not disturb others. Now, we will see that since we are talking of lossless filters, the filter elements or the elements of the filter network, they need to be reactive, there should not be any resistance with that. So, these reactive networks who has this property that all the band of frequencies are passed or transmitted unattenuated, and a band of frequencies are rejected completely or stopped, that two-port network is called filters. Scientist J. A. Campbell and O. G. Jobel were the stars to look into analysis of these filters. They were engineers in Bell Telephone Laboratories, and from that date the RF filter has been designed, developed and used extensively in all applications where you need to play with RF frequencies. Now, all these filters are symmetric network, composed of symmetrical network sections. All of you are familiar with two-port networks. Now, we will start this analysis because this is a, in BTech course this is included, but many times this is not so well understood. That is why we are, this first lecture is a refreshing of that. The thing is, the lecture topic is image impedance based lossless RF filter design. Now, we will introduce image impedance a bit later, but I start with a two-port reciprocal network. A two-port reciprocal network, you know that a port has two terminals. So, let us say this is my port 1, this is my port 2, another two terminals, I call it port 1, port 2. I have some network here, electronic network. So, I describe, you know that any two-port network, electronic network can be described by several parameters, either Z parameter or Y parameter or H parameter or G parameter, etc. Also, you know that there is a parameter called ABCD parameter, which I take here. Why? Because this filter, finally I will arrive at filter. So, this two-port network will be filter. Now, this is always in cascade. It is connected in the input side to something, it is connected to output side with something. So, it is in cascade. So, we need to find out how the RF signal transmits here through this network. So, ABCD is a transmission parameter, all of you are familiar with its definition, etc. So, I will use ABCD parameters for describing this two-port network. Also, this model, you see, this is not a low frequency model. Here this voltages, currents, etc., they are TM mode, but the transmission line is distributed. It is based on distributed line parameters. So, voltage, currents, etc., are actually there are voltage waves. So, there is always at the, depending on the load and the level of impedance of this network, there is a possibility of reflection of waves. So, keeping that in mind, we know that if there are reflections, then actually the model is a distributed line model where voltage incident waves and reflected waves both are present. So, voltages, currents, they are complex in nature in this type of circuits. This is called RF circuits. So, our port voltages, port 1 voltage, port 2 voltage, port 1 current, port 2 current, they will be also phasor quantities, they have both magnitude and phase. So, they are complex voltages and complex current. So, I start that let this port 1 has a voltage given by V1. Generally, we say that complex voltage we prefer to represent by V with a tilde with a tilde at the top, that is complex voltage. But here, since all the quantities are complex voltages, I do not use this thing, I do not put that tilde, I say V1, but you should understand that this is actually a complex voltage. If you want, you can have your own notation V1 with a tilde on top. So, at port 1 the voltage is V1 complex voltage, and the current entering port 1 is I1, again a complex current. Similarly, at port 2 I have the terminal voltage as V2 as shown, and I have current which is leaving this port I2 complex current. Please note this direction of current. Generally in all other 2 port parameters Z, Y, H, G, etc., the I2 is the current entering the port, I1 is current entering port 1, I2 is current entering port 2, but in transmission parameters, since actually the wave transmits like this I2 is directed away from the port. Now, this obviously I will connect with a source. This is the network, this ABCD parameter, these 4 parameters completely describes the network. I need not know what is inside. If I know ABCD, I know how the network will behave when I excite with a particular voltage and current. Now, I connect with this a voltage source, complex voltage source, obviously an AC source, we are not talking of DC voltages, it is an RF circuit. So, I call that generator as Vs, an AC source with assumed polarity like this, and the internal impedance is Zs. So, voltage source with internal impedance Zs is connected to port 1 to excite this network, and there will be some other, as I said, some other thing, some other electronic blocks, electronic 2 port blocks, but for this we assume that that is acting as a load impedance to this. All these load impedance and source impedance, they are complex in nature, generalized impedance. Okay. So, once I have this, you all know that I can describe this V1 I1 and V2 I2 with the help of an ABCD matrix. So, I can write V1 by I1 is equal to A, B, C, D, V2 I2. Now, with this loaded condition, that means with the source voltage and so generator and load, I can write that Vs, if I apply Kirchhoff's law around this loop, I get Vs minus Zs I1 minus V1 depending on the polarity I have shown is equal to 0. So, I get V1 is equal to Vs minus Zs I1. At the port 2, I can write V2 minus I2 ZL is equal to 0, that gives me V2 is equal to I ZL I2. So, I have in V1 and V2 I have incorporated the generator Vs voltage, Zs internal impedance of the source and load impedance ZL. Now, we can proceed and write the ABCD parameters. Actually, our objective is we will design all these RF filters, they are made with reciprocal components generally. Generally, you know that we do not use magnetic materials like ferrites etc. to design a filter. So, this because they becomes bulky and lossy etc. So, we are assuming reciprocal 2 port network. So, with this 2 port network I will add a condition that it is a reciprocal network. Now, I will see that what this reciprocity demands from this network, that means ABCD, what is the condition that is imposed if I use reciprocity. So, for that what I will do You see what is reciprocity? That if I have a multi-port network, at one port if I excite, if I give some excitation, and at some other port if I find the response, then everything network remaining unchanged. If I just change the excitation to the response port in earlier case and see the response in the original excitation port, I will get the same response. That is called reciprocity, all of you know. So, I will do that, but you know that characterization of a network is always in terms of impedances. Voltage, current, etc., they can be anything, but impedance of the network is the fundamental quantity which characterizes the network. So, here I will do that suppose at this port 1 I am exciting with Vs, at port 2 the response I am getting in terms of I2. So, what is this transfer impedance? The transfer impedance is Vs by I2. Then I will find this quantity first, then what I will do, I will excite the port 2 with this same voltage Vs, and keeping this, obviously this Z dash should be kept there. I will excite with Vs and I will find what is the current, that time this I1 current, that will be the response. I will find that ratio and what is the transfer impedance for that. That means when it is transferred from port 2 to port 1, what is the impedance. Now, if the whole network is reciprocal, these two should be equal. The transfer impedance in case 1 and transfer impedance in case 2 should be equal. So, from that I will try to find out what is the relationship between A, B, C, D, so that this network is reciprocal. So, towards that, first I keep this same circuit diagram. First let us analyze what is the transfer impedance in this case. So, as you all know that I can write V1 is equal to A V2 plus B I2, and V1 already here you see I have related V1 to the excitation voltage Vs. So, I will put that and then I will get Vs is equal to Zs I1 plus A Zl I2 plus B I2. Finally, by manipulating you get this becomes I2 into A Zl plus B plus Zs Zl C plus Zs D. So, I have got my transfer impedance Vs by I2 is equal to A Zl plus B plus Zs Zl C plus Zs D. So, you see the transfer impedance depends on all A, B, C, D 4 parameters of the 2-port network. Also, it depends on my internal resistance of the source excitation and the load impedance. I leave this here, let us consider this as equation number 1. Then I change the scenario, that means I exchange the excitation and response. So, I have the same old ABCD network. I am not exciting at port 1, I will excite at port 2, but all other conditions are to be kept same. So, my Vs, the same excitation that I gave in earlier case, I am connecting here, but the internal resistance I will have to now consider as ZL, because I cannot change any impedance of this whole network, loaded network. So, Vs is the only voltage source, ideal voltage source, its internal impedance is taken care of in ZS, it will come in the input side or port 1 side. So, this now I will call, since this is generally we call port 1 as the excitation port. So, now I can call this port as V1, this is port 1, but to avoid confusion I will call that V1 dashed. So, this is my V1 dashed port voltage here in this new scenario, because Vs is connected here. So, I will have to call it V1, but I am calling it V1 dashed. Also the current will enter. So, always from excitation port current enters. So, I1 is here I1 dashed, I am calling. ABCD is unchanged because I have not changed this network anything, but this outside condition have changed. So, the current that will come out of it, I will have to call it I2 dash. In transmission parameters, the current enters through the port excitation port, leaves the response port. So, I2 dash is like this, and then I will have to keep that internal impedance. In the first case it should be same here, otherwise the reciprocity won't hold. So, ZS is here and I will call this port voltage as V2 dashed. Okay. So, now just ABCD parameter is unchanged. So, can I say that in terms of ABCD parameter I can represent V1 dashed, I1 dashed, V2 dashed, I2 dashed. How? I will write V2 dashed, then you see compared to the previous case it has changed. So, I minus I2 dashed because direction change, last time it was oppositely directed, is equal to A, B, C, D, V1 dashed and again minus I1 dashed. Previous case and this case, the voltages V1, V1 dashed, V2, V2 dashed, their polarity, assumed polarity are same, but currents are opposite polarity compared to the earlier case. Since I will compare these two cases, so compared to the earlier reference, now my I1 dashed and I2 dashed are negative. Now I can include the excitation part as I have done before. So, I can write by applying KVL here, Vs minus I1 dashed ZL is equal to V1 dashed and ZS into I2 dashed is equal to V2 dashed. Okay. And we can as usual write the ABCD parameters from this equation. I can write V2 dash is equal to A V1 dash minus B I1 dash and minus I2 dash is equal to C V1 dash minus D I1 dash. I will do that. V2 dash is equal to A V1 dash minus B I1 dash and minus I2 dash is equal to C V1 dash minus D I2 dash. Once I have this, once I have the excitation, these two coefficients, these two equations, I can now find the transfer impedance. What will be my transfer impedance? My transfer impedance is Vs by I2 dashed. So, by manipulation, simple manipulation, you get ZL A plus B plus ZS ZL C plus ZS D by AD minus BC. So, I have earlier got Vs by I1 dash, now I got Vs by I2 dash. So, they should be equal. Reciprocity implies Vs by I2 in the first case should be equal to Vs by I2 dashed in the second case. So, if you do that, you will get the relation AD minus BC is equal to 1. All of you know this, that for a reciprocal network ABCD parameters have this relation, but for us it has a particular bearing, an important bearing, that you see for a two port reciprocal network, I do not need 4 parameters to represent the network. Since A, B, C, D are connected like this, 3 parameters are sufficient. Out of these 4 ABCD parameters, 3 parameters are sufficient to characterize completely a network. Minimum 3 parameters will suffice. The rest I can find from the fourth one I can find from this. So, 3 parameters needed to represent a reciprocal two port network. Now, here you see ABCD is not suitable for me when I will go to filter design. Why? Because what is A? If you see the definition of A, from here you can see that it is a voltage ratio. So, A is a voltage ratio, D is a current ratio, B is a transfer impedance, and C is a transfer admittance. But as I said that I require to specify that what will be my pass band of frequencies, what will be my stop band of frequencies. So, I cannot impose by on this voltage ratio, current ratio, transfer impedance, transfer admittance, I cannot enforce that. So, I need to search parameters which will characterize the network, but which will also take the specifications of filter from me. So, first we will say that instead of this voltage ratio, current ratio, can we have some impedance description of this network? Can we have some impedance description of this network? That will lead us to the concept of image impedance. So, we will see the concept of image impedance. I do not know whether you have heard this term. This image impedance is an important concept in developing filter theory or many other applications, electronic network applications. This image impedance we will take up in the next lecture, and we will see that how this image impedance will solve this problem. We will try to find out what are the parameters that will characterize my network and on which we can specify the pass band, stop band, those descriptions or specifications. Thank you.